Okay. So today's topic will be nuclei or nuclear physics. So we'll start with that. See, atomic. What is atomic number? What is atomic mass? What is AMU? Atomic mass unit. Already this you studied in chemistry in grade 11 chemistry first lesson, atomic structure. So the same definitions will be repeated again. So after doing that, we have discovery of the neutron. Okay, anyways, that is not required, but we have relation between atomic mass, atomic number, and neutron number. Then we have size of nucleus. How did we find out the size of the nucleus? And there is a formula for that. Then we have E is equal to mc square. Then we have mass energy equivalence relation, that is E equal to mc square, which was found by Albert Einstein. Then we have binding energy. So after that, there is a graph which is very, very important. Next, we have nuclear forces, and then radioactivity, discovery of radioactivity by Henry Becquerel and Madame Curie and all. After that, we have law of radioactive decay. Okay, law of radioactive decay. Then I think they deleted two topics here: half-life period and average half-life. But anyways, I'll give the explanation of that one. Then we have alpha, beta, gamma decay. 3 decays are there, which are very easy. Actually, they should not have been deleted. Very simple to understand. Next is the last part will be nuclear energy. In that nuclear energy, we have nuclear fission and fusion. And then nuclear fission, one of the example will be nuclear reactor. Okay, which is the last topic of this lesson. Thermonuclear fusion is also there. In future, we'll be having fusion reactors. Okay, these are the topics which are there in this lesson. Now, we'll start with the first topic, that is atomic number. We'll start with the first topic, atomic mass. Okay, an atomic number. So what is atomic number? What is atomic number? Atomic number is denoted by Z. Okay, number of protons in the nucleus. Number of protons present in the nucleus. Present in the nucleus is known as atomic number. Like suppose, example, when I write C612, here 6 is the Z equal to 6 in this case. Next is atomic mass. Atomic mass or mass number. Mass number, that is capital A. So number of protons and neutrons. Number of protons and neutrons. Number of protons and neutrons present in the nucleus. Present in the nucleus is known as proton, that is the atomic mass or mass number. So here, if you take the example of this, is C612. If I take the same example here, so atomic mass is what? A is equal to 12. Okay. Now, how will we calculate the number of neutrons? Number of neutrons, N. Number of neutrons is calculated in this way. That is what? N. So we have the formula here. A equal to Z plus N. So N is equal to A minus Z. This is the formula to calculate the number of neutrons. Is that clear? Is the formula to calculate number of neutrons. We have the formula. Suppose XZA. Okay, X is the symbol. X is the symbol of the element. This is symbol of element. Okay, and Z is atomic number. This is atomic number, and this is atomic mass. Okay, atomic number and atomic mass. So this is the way we solve it. Now, next is, here we have one AMU, one atomic mass unit, one AMU, one U, or we also write one AMU is what? Atomic mass unit. How do you define atomic mass unit? Atomic mass unit. How will we define this? Atomic mass unit is defined as 1 by 12 the mass of carbon C612. 1 by 12 of mass of C612. Means if you divide C612 into 12 parts, like suppose if this is C612, example I'm taking 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 parts are there. So this one part is known as AMU, 1 AMU. If you break the C612 atom into 12 parts, then one part is known as 1 atomic mass unit. So what is the value of one AMU? Is exactly equal to mass of the proton 1.66 into 10 to the power of minus 27 kg. That is the mass of proton. Okay, next one. We will go with mass of neutron and so one AME value, mass of proton and mass of neutron also will solve. So mass of proton is 1.00727. Mass of proton is 1.00727 U. Mass of neutron is how much? 1.00866. 1.00866 U. 1.00866 U. So that is the value of mass of neutron. Okay. Is that clear?
Sir?
Yeah, yes, tell me.
Sir, but mass of proton is 1.6 into 10 raised to minus 27, right?
Yeah, so better I will write the full value for you, for your convenience. Okay, 0. It is 1.66000539. 0539 into 10 to the power of minus 27 kg. Okay. Is that clear? So this is the actual value of one atomic mass unit. So if you want to find out the mass of proton, just divide it with that. Then you will get the value 1.00727 U. And mass of neutron also. Write the mass of neutron. Mass of the mass of electron is 0.000. Mass of electron is 0.00055 U. Okay. If you want to write mass of electron, proton, and neutron in terms of atomic mass unit, you have to write in this way. Is that clear? Is this clear all of you?
Yes, sir.
Okay. So. One U is equal to mass of C612 atom. C612 atom divided by 12. So 1 U is equal to mass of C612 is 1.99 into 10 to the power of 26 minus 26 divided by 12. How did we calculate this mass of one atom? We have to go for Avogadro number then. Got it? We want to calculate mass of one atom. See, in one, if I take 12 grams, of carbon, how many atoms are there? Go to mole concept, grade 11. If I take 12 grams of C612, I will be having Avogadro number of atoms. Is it not? Avogadro number means 6.00 into 10 to the power of 22. Now I want to find out the mass of one atom. So what I have to do? If 12 grams will give so and so mass, 12 grams will give so and so thing. So one atom with how much? You have to cross multiply that. Then you will get this value 1.99 into 10 to the power of 26. Then divide by 12. So then you are going to get one atomic mass unit is equal to how much? 1.660 into 10 to the power of minus 27 kg. Is that clear?
Yes, sir.
Yeah. Okay. Please note down this. Then we'll go. Now. Now. Now here, suppose example, chlorine, there are two isotopes. Okay. Example, that is relative abundance. Relative abundance, and next is isotopes. What are isotopes? What are isotopes? Isotopes means atoms with same atomic number, but different atomic mass. Same atomic number but different atomic mass is said to be isotope. So what are the examples of isotope? H11, H12, H13. Okay, these are the isotopes. Okay. Now, so here we have chlorine. So we have chlorine, for example, it has two isotopes. Okay, that is how much? That is example of chlorine. It has two isotopes. What are they? One is 34.98 U, and the second isotope is 36.98 U. Okay, these are the two isotopes. Now, so here the relative abundance is how much now? Means which is available in the nature. Relative abundance is how much? That is 74. This percentage is 74.75.4. 75.4, and the second is 24.24.6. This is the availability in the nature. Means this much percentage. If you take 1 kg of example, if I'm taking 1 kg of chlorine from the nature, then 75.54% will be this isotope, and 24 or approximately 25% will be this much. So how do we calculate this one? The average atomic mass or average mass. Average mass, how will we calculate now? This is 3475.4 multiply 34.9898 plus 24.6 into 36.98 divided by 100. So then we will get how much? 35.47 U atomic mass. Is that clear now? So that is about the way how will we calculate the average atomic mass. Is that clear? So that is why if you see chlorine, you don't have two values in the periodic classification table. It will be only one value. Yeah, it is 35.5. Is it not? When you look at the periodic classification table for chlorine, it is only one, 35.5. It's not like there are two actually. One is 35, one is 37. So they don't write either 35, they don't write even 37. They wrote 35.5. Is it not? Did you question your chemistry teacher in your grade 11? Why it is 35.5? Yes?
No, sir.
No. See, there are two isotopes of chlorine. A simple example, there are two isotopes of chlorine. One is 35, one is 37. But they are writing the periodic classification table 35.5 for chlorine. Is it not? Everyone knows about it. But how did they write that? They take 1 kg of chlorine, and how much percentage is they separate the two isotopes. 75% they found 35, and 25% they found 37. Then they found out the average mass. That is how they wrote that 35.5 in the periodic classification table. That is how all the masses are written. Sometimes not only an element like hydrogen is there are 3 isotopes, but still he's writing 1H1. See? But they wrote right 1H2 or 1H1.1, nothing like that. Why? Because 99.8% is 1H1. If you take 1 kg of hydrogen, in that 99.8%, 99 point means almost 100. That much is 1H1. The remaining is 1H2 and 1H3. So that is why we don't write 1H 1H1.1 or 1H1.5 like that. Got it now? Is that clear?
Yes, sir.
So that is the availability in the nature. Now come back to chlorine. Sorry, carbon. Carbon, we have C612. We don't write C613, C614 also. Why? Because if you take again 100%, like 1 kg of carbon, 99% is almost carbon and the C612, and the remaining is C613 and 14. Got it? Is that clear?
I got it.
Okay. So we'll go to the isobars and isotones also. Okay. So isobars, what is isobar then? Can anyone say what is isobar? Yes. Isobar means atoms with same mass number. With same mass number of different elements. Example is what? Example for isobars is what? C614 N714. This is the example. Mass number is same, but atomic number is different. Next is what? Isotones. What is isotones? Okay, atoms with same number of neutrons. Atoms with same number of neutrons is known as isotones. What is the example of isotones? Like we can write C613 N714 oxygen 815. See the example 13 minus 7, 13 minus 6 is 7. Number of neutrons are same. 14 minus 7 is 7. Again 15 minus 8 is also 7. So we have same number of neutrons. Is that clear? Once again, isobars means atoms with same mass number of different elements, C614 and N714. Isotones means atoms with same number of neutrons, C613 and N714 and oxygen 815. So just take the subtract it, you will get the values. Clear?
Yes.
Now we'll go to size of the nucleus. Size of the nucleus. Size of the nucleus was found by the experiment Giger and Marsden. Giger and Marsden, these two people, they have found out, they were doing that is alpha scattering experiment. That is also known as gold foil experiment. When they were doing this gold foil experiment, they want to find out the closest approach of alpha particle, to the nucleus. What is the closest approach? So like you already studied this. Okay, this is the gold nucleus. So now what happens? So this is 1 in 10,000 will have head-on collision. Okay. So the next one is what? Okay, so this is the closest approach. How much is the closest approach? You can see. So they want to find out the closest approach. With that experiment, they found any alpha part with the kinetic energy. If the kinetic energy of alpha particle, is 5.5 million electron volt, MeV, million electron volt, is about the closest approach. Okay, the closest approach. Why I am going in detail? Because this type of questions they can ask in assertion reasoning. That's a problem, or MCQs. Okay. Yeah.
Yeah, sir. Okay.
Now, so now here R is the energy. How much is the closest approach? The closest approach is 4 into 10 to the power of minus 14. 4 into 10 to the power of minus 14 meter. They found out from this experiment. Okay. So Giger and Marsden. Giger is two different people. Okay. Again, Giger and Muller is also one more scientist. They find the Giger and Muller. They found out the alpha detectors. Okay. That is radioactive detectors. What we can say, alpha, beta, gamma detectors. Okay. So so with that, they found out that there is a formula. R is equal to what? R is equal to, they found out the radius. R is equal to R naught into A to the power of 1 by 3. R is equal to R naught into A to the power of 1 by 3. What is R naught? 1.2 into R naught is the radius. In the previous chapter, we studied this. What did we study? Radius of the atomic. Okay. So radius of the first orbit. Radius of the first orbit is how much? 1.2 and 10 to the power of minus 15, or unit radius. We did this in the previous topic. Yeah. So that is equal to what? R naught is equal to minus 15. So therefore, so how did they calculate this? They use the formula in liquid